Okay, so first let me say thanks very much to the organizers for the invitation to come visit, give a talk. Looking forward to kind of the rest of the meeting. So I thought what I'd do is to introduce the subject of what I'm going to talk about. I thought I'd first start with some artwork. So this is artwork that was put together by an artist that kind of helped us out with some of our papers. So here is a picture of one of the things we put out. This is going to be about things having to do with the swampland cobordism conjecture. So I'll tell you what that is, and specifically in the context of type 2b dualities. So the dualities that kind of govern are strong and weak dualities in 2b supergravity and string theory and F theory. So here you don't have to kind of memorize the plot or the map or anything. But the idea is basically to kind of calculate various kinds of cobordism groups. Again, I'll tell you what those are in more detail a little bit later. But then as a tool to understand aspects of non-perturbative features of string theory, especially in the context of dualities. And 2B dualities is kind of the tip of the iceberg. There's also other ones that you can talk about, in particular so-called U dualities. They specifically show up in toroidal compactifications of M theory. And this is another map that our friend Paco Giudice made, kind of illustrating how to kind of move around in this kind of big, vast world of dualities, especially in the context of U dualities and cobordisms. And we referred to this as utopia because it involves U dualities. And that appeared earlier this year. And then, of course, the two maps combine like this. Very nice. The region that I'm going to be talking about today is kind of a little corner inside of, if you like, the U dualities, a piece that was not really that explored early on. And I'm going to refer to this as Pintopia. And the reason is because what we're going to do is take some of the duality structures that we studied in the context of U dualities, and then looking specifically at what happens with structures having to do with the fermionic degrees of freedom. And the motivation here is to not just study, say, supersymmetric backgrounds, where U dualities have been very, very well understood now, but also to kind of get ready for more general situations, in particular ones that may not have any supersymmetry being preserved. So down here, this is higher utopia, spinors, and omega 1, which is what we will refer to as kind of the first Cobordism group, and that's the one I'm going to focus on in what follows. Okay, so it's based on these three papers. Here's the Tubordia one, here's the utopia one, and this is kind of the spin or pin plus lift of some of these considerations called Pintopia. And for the most part, I'm going to focus on this last one, or the top one, the one that just appeared a few weeks ago. But I'll, of course, be making reference to this as well as some other papers. Sorry if I forgot to cite your favorite paper in the slides. Hopefully, it's more complete in the papers. But if I forgot either one, please let me know. So this talk is going to be about U dualities. I've already mentioned that. I'll review what I mean by those in just a moment. It's going to be about this so-called swampland cobordism conjecture. In particular, this kind of intriguing statement that the bordism groups of quantum gravity are supposed to be trivial. I'll explain what that means. And kind of one of the consequences of this that's going to come out is that we're going to see that once we put some of these ingredients together, we're going to find predictions for stable, non-supersymmetric branes, new kinds of branes that you may not have been able to access using, say, world sheet techniques or other kind of supersymmetric duality considerations. So that's going to be one of the outputs of what's going to come out of these considerations. And there's, of course, a nice interplay between all three of these, and we'll see how that goes in just a moment. So I'm going to start up here with kind of U dualities, and then I'll proceed kind of to the bottom left, swampland cobordism, and then wind up with these RP branes. And the R here refers to reflections. As we'll see, there's a geometric interpretation of these things in terms of reflections in a kind of internal direction. Okay, so what are the U dualities? So this is something that's been appreciated since kind of the late 1970s and onwards. It played a very prominent role in the duality considerations in the mid-90s as well. So you take maximally supersymmetric non-chiral gravity with 32 real supercharges in the spinor representations of the spin group. And it tells you things about the non-perturbative data of the effective field theory in D space-time dimensions. And I'm going to write the U duality group in this suggestive form We're not actually going to directly use this, but it's at least a very nice geometrically motivating way of writing it. It involves this SLD, which we can think of as a kind of geometrizing certain kinds of diffeomorphisms, and then this T-duality group, spin d minus 1, d minus 1. This product here, this bow tie thing, should be thought of as a generalization of the semi-direct product, in which there's an automorphism of one of the factors acting to the right and one acting to the left. Okay, so what is this bow tie product in a little more detail geometrically? So it involves this SL little d and spin d minus 1, d minus 1. So to motivate where this thing is coming from, consider M theory on the following spacetime. So remember, big D plus little d have to add up to 11 because I'm talking about M theory. SLD is going to be about just the large diffeomorphisms of this d-dimensional torus. So you might be familiar in the context of, say, type 2b or F theory. The famous SL2 has this nice geometric interpretation as being an action on kind of the F theory torus. This is just a generalization to the d-dimensional effective field theories we get in supergravity. What about this part here? Well, it involves a d minus 1 dimensional kind of split form of the spin group. Why is it d minus 1? Well, we take M theory, we go down on a circle to type 2a, and there we're talking about the T-duality group of kind of the remaining space-time directions. So, and finally, why is it spin as opposed to SO? You may have seen it written as SO earlier in many treatments. Well, you have to have it be spin just because it had nothing to do with spinners in the space-time, but just because the Ramon-Ramon states of the type 2 theory transform as bispinner representations. So these are, of course, bosonic degrees of freedom, but they're transforming in bispinners. So you have to include that in order to have this. If you did it with SO, it wouldn't have gone through. Okay, so here are the U-duality groups in the form that we're going to be using them more precisely. So if you're down in 9 dimensions, you have a 2-dimensional torus, and you can clearly see the famous SL2. If you are on a 3 torus, you get something a little more than SL3. You actually get this kind of bigger group, and down it goes. And these are referred to as kind of the split real forms, for example, of the exceptional groups. So they're not the compact real forms that you have, say, in kind of higher dimensional grand unified theories, but rather these split real forms. So in particular, they're non-compact. Okay, so why are these so exciting to look at? Well, it provides you, as was kind of recognized especially in this paper by Hull Townsend in '94, and then follow-up work, especially Witten's paper from a little while later, that it provides you non-perturbative access to kind of the supersymmetric and BPS sectors of quantum gravity, which is, of course, very, very useful. And it's difficult to find kind of tools to kind of study that. Now, the typical setup is in the d-dimensional effective field theory, you're usually working in a background which is kind of Ricci flat, usually actually just flat space-time or just some torus. And moreover, you assume various nice structures that you can define spinners and so on the d-dimensional effective field theory. A natural question, though, is what if it wasn't flat? What if it wasn't spin? What if it wasn't even non-supersymmetric? So what we're going to be doing is kind of revisiting the structure of these U-dualities in that broader setting. So, okay, I already said this, but what happens if it's not flat, not spin, not supersymmetric? Can we still talk about, or what is the appropriate U-duality structure in these more general settings? So to kind of motivate what's going on, I'll just point out that in many backgrounds of interest, the kind of effective field theory space-time doesn't have to be spin. It doesn't have to support spinners by itself. Rather, it supports what we would refer to as kind of spin-twisted duality bundle structures. To illustrate, I'll consider, if you know F theory, great. If you don't, not a problem. Let's take this 10-dimensional space-time. So we have our 6-dimensional space here. CP2 is just an interesting 4-manifold. But the crucial point is that it's not a spin manifold. It doesn't admit spinners by itself. Rather, it has this other notion, which we call spin-C structure. So it's almost spin, except you have to keep shifting by some additional U1 bundle. Now, how does an F theorist actually make sense of such 10-dimensional spacetimes? Well, from an effective field theory point of view, they recognize that there's actually a non-trivial duality bundle in the game. And if you take into account the duality bundle plus the spin-C structure, then you find killing spinners, not really on CP2 itself, but rather on the total space defined by the geometrized duality bundle, written as this F theory torus, over the CP2. So this kind of automatically geometrizes this thing. But if you're just effective field theorist working in 10 dimensions and you don't know about, say, this geometric thing, you could just say, well, the fermions are actually coupling to something bigger than just the spin C structure. They're actually coupling to spin C plus some duality bundle. So what we're going to be after is finding the appropriate gamma, some duality group, such that when we look at our spinners, in particular our fermions, they're going to be written as some spin structure times some duality bundle, and then we're going to quotient out by some putative diagonal Z2. And the way to think about this is, imagine we have, say, some different covariant derivative. We're going to have the spin connection plus a duality bundle connection. And we're going to try to figure out what the appropriate gamma has to be in order to make sense of spinners and fermions on more general kinds of backgrounds. In particular, we know it's not going to be just the U-duality bundle structure. Why? Because I already know it didn't work that way as easily in the context of CP2. OK, now there's one more thing on top of just talking about spinners that we're going to need to take into account, which is that actually the dualities need to take into account one more symmetry, which isn't manifest in the usual way of presenting the U-dualities. And that's a pretty down-to-earth symmetry from the point of view of, say, type 2a. Let's just take M theory and go down on a circle. There's one more thing we could talk about, which is reflections on the internal circle. This is an admissible symmetry transformation in these kinds of backgrounds. It corresponds to taking, say, the internal coordinate and flipping the sign. So it's orientation reversal from the point of view of the circle. What does this look like from the point of view of type 2a? It's the left-moving fermion parity number acting on the degrees of freedom in the 10-dimensional theory. That's not in the U-duality group. It's a bigger symmetry beyond that, just in the U-duality group. And I think this was kind of first, this spin lift thing was first appreciated, I think, kind of very sharply in this Pantev-Sharp paper. And then this reflection statement, souping up the spin lift, was in this paper by Tachikawa Yonokura. And then we studied it in various incarnations, both in 2B dualities and U-dualities in this sequence of papers. So how do you lift GU? There's going to be two different lifts that we're going to have to try to combine. One is what I'll refer to as the spinner lift. I'll write that as a GU tilde. And you should be thinking about this as kind of like the spin cover of, say, an orthogonal group or something like that. So the same way that spin 3 or SU2 covers SO3, same idea here. This will be the G tilde U here. There will also be so-called reflection lift, where we're going to allow ourselves to also talk about GU including more transformations that also include, say, internal reflections when we have, say, a toroidal compactation. And then the final thing is this kind of big thing over here, GU tilde plus, which I'll refer to as taking into account both reflections and spinners. And when you start talking about reflections with spinners, you get what are called pin lifts of the corresponding groups. And the reason why it's plus rather than minus, I'll explain in a little bit later. So basically, what we're going to be after is figuring out structures associated with this pin plus lift. OK. So let me just explain how it works in the case of SLDZ. So that's the case where we just talk about, say, the large diffeomorphisms of the d-dimensional torus. So just purely geometry. We're not talking about the T dualities yet for type 2. What would we say in this case? So here's the procedure. And basically, the elements of that procedure were already kind of spelled out at some level in this Pantev-Sharp paper. But we kind of revisited how to do it for a broader set. What do? You look for the maximal compact subgroup inside of SLD. And that's just SOD. SOD has a very nice spin lift. That's pretty straightforward to figure out. That's just the usual spinners. And that spin lift induces a corresponding lift on SL when you're working with the reals. That in turn induces one when you restrict back, you pull it back onto just the integers. So you get, so sorry, I realize I'm using the short exact sequence notation. This just means that the images of the kernels, if you don't want to think about it like that, take the middle thing and divide by this. It's just telling you that spin D mod Z2 gives you the thing on the right. And you do it for all of them. So this one, quotient by Z2, gives you the thing on the right. So we have this SLDZ tilde lift basically induced directly from finding the maximal compact subgroup of SLDR. How about the reflections? Well, you can include any reflection you want. It turns out that if you include one of them, then by conjugating with the SLDs, you can get to all of the other ones. And then there's, again, a corresponding short exact sequence. In this case, SLD embeds inside of just GLDZ. So you allow yourself not just the determinant 1, but also the determinant -1 matrices. And then the determinant map in the short exact sequence is just this Z2 here. And so a fancier mathematical way to write that is some Z2 semi-direct on SL2. But the key point is that you kind of go from SLD, morally speaking, to GLDZ. So you allow yourselves orientation reversing diffeomorphisms. Okay, and then putting it all together, you get this so-called pin plus cover of GLDZ. Now, the plus here refers to the fact that the reflection squareds, when they're acting in the appropriate lift, squares to 1. If you're familiar with how fermions can kind of do funny things under reflections, it didn't have to square to 1. Another option is what we'd be calling where it squares to -1 to the f, so in other words, fermion parity. That would have corresponded to the pin minus lift. And for reasons having to do with M theory being defined more on pin plus structures, we're going to stick to this r squared equals 1. And that's what's dictating this pin plus lift right here. So this is how it goes for just the SLD. And now what we'd like to do is do the exact same procedure for the more complicated case of more general U dualities. So how's it going to work more generally? So again, this semi-direct language is just saying GU tilde, quotient by Z2, gives us GU. And you do a similar thing with these reflections. We're going to be looking for finding the corresponding GU tildes, GU Rs, and then putting it all together, this GU tilde plus. Okay. Now, the first non-trivial statement is that actually there are non-trivial Z2 extensions for all of these cases. And the crucial point here is that the GU, the one that you start with, is actually non-compact to begin with. If you had started with, say, the compact form of E8 or E7 or E6, then you could do a Z2 lift, but it would be kind of a stupid and trivial one. You would just take a Cartesian product with a Z2. Okay, so here's a little more data. Here are the different compact subgroups for the different U-duality groups. Here they are. And then the corresponding Z2 extensions. I mean, the crucial point is basically to look at this compact subgroup piece right here, and then to figure out the corresponding spin and pin plus lifts for these compact subgroups. That's basically uniquely determined. And once you know that, then the rest of it kind of follows just from how it embeds appropriately inside of the U-duality groups. Okay, so the interesting point is that in all of these cases, you get a non-trivial set of Z2 extensions. Okay, so that's all I want to talk about for U-dualities. Now I want to put it together with the Swampland-Cobordism conjecture. So you might ask, what do these two things have to do with each other? That's what I'm going to tell you about next. Okay, so let me just begin with the Swampland-Cobordism conjecture. This is this intriguing statement that the Bordism groups of quantum gravity are trivial. And one way to think about this statement is that the idea is that you're given any spacetime, the conjecture is that you can basically terminate it or end it with some boundary. So the provocative claim is that the Cobordism groups of quantum gravity are trivial. There's many questions you could ask about this. For example, what do you mean by quantum gravity? What do you mean by the Bordism groups of quantum gravity? And if you can't define them, then what is this good for? What we're going to see, however, is that even though we cannot define this thing directly, the conjecture is actually far from being vacuous. It's actually very powerful because we do know how to calculate Bordism groups in many interesting situations. And using that, we can actually predict the existence of new objects. So the procedure or the algorithm is you keep adding new objects into the system, to the physical theory, until you find basically everything can be terminated. Every possible spacetime can be terminated. So that's what makes this a very powerful conjecture, that you can calculate Bordism groups in many non-trivial cases. And by calculating that they're non-zero, you predict a new object. So I'll explain how that happens in just a moment. So just to kind of motivate why this isn't just some ridiculous conjecture coming out of nowhere, as already shown in this paper, in the original paper, you can use this to basically post-dict the existence of things you already knew about. So for example, D-branes and orientifold planes, things you knew about from kind of other avenues. For example, worldsheet techniques. There's many non-trivial checks. I'm only going to list a few relevant from my talk, so I'm sorry if your favorite paper is not here. So there's some n-fold permutation of these authors involving dualities and supersymmetric backgrounds, as well as non-supersymmetric backgrounds, I should say, as well as predictions for kind of non-supersymmetric things. So for example, walls between type 2A and type 2B, so-called reflection submarine, something I'll come to in just a moment, and other things, as we'll see. So what's a cobordism and what does it have to do with any of this? So cobordism is basically some equivalence class between different manifolds. So we say that two manifolds, say X and X prime, are cobordant if there's a single bulk manifold which has boundary given by this X and X prime. And I've indicated you can stick a bundle, a non-trivial structure over this bundle over X and maybe it's bored into another one over here. So it doesn't just have to be about some manifold. It can be a manifold equipped with appropriate bundles. You could think about this as saying, I want to have gauge theory defined on X, and I'd like to know what kind of gauge field configurations can also interpolate from one boundary to the other boundary. Okay, so it's a group. Here's the 0 element. So you can basically just glue this little nub onto anything and it won't change your answers. Here's addition. So if you added the nub on, it would kind of cap it off like this and do nothing. So you add 2 elements like this and you get a third one out like this. And you can check that it kind of satisfies all the rules of a group. So why is it interesting to have a non-zero Cobordism group? Suppose you have found one. As I'll explain in just a moment, this means that you would have a global symmetry. So in the context of gravity, this would be an indication that something has gone wrong in your theory, or you haven't done a proper job discussing the gravitational theory. So consider gravity down in our d-dimensional effective field theory and glue in one of these Cobordisms into the spacetime. So we'll split the spacetime up into like an RP plus kind of the remaining direction. So there's some tube that kind of connects in like this. What does this thing look like from the point of view of the d-dimensional effective field theorist? Well, it means we put in some RP dimension, there's some p-dimensional defect that fills some big region inside of our d-dimensional spacetime. And so it looks like there's basically a global symmetry acting upon this p-dimensional defect. The exact charge and so on is captured by looking at kind of the Pontryagin dual, or this homomorphisms of omega k into U1. That's not so crucial. The key point is that there is a globally conserved charge associated with having this manifold that you cannot kind of deform away. The whole point of saying you have a manifold you can't deform away means that there is a global symmetry. It's carrying a globally conserved charge. Now, this fits into the paradigm of kind of the generalized symmetries in quantum field theories. And so the idea here is that we have some extended defect, and there's some topological operator linking with it, which kind of tells us how a symmetry will act upon it. And the thing that we've just built using our p-dimensional defect is this red line, or this red submanifold. But remember that in gravity, we don't expect there to be any global symmetries. And you can interrogate this by looking at, say, black hole backgrounds, wormhole backgrounds, and so on. And especially in the context of, say, holography like ADS-CFT. So you might ask, OK, why am I now talking about having global symmetries if I don't expect those to kind of survive in the context of a gravitational theory? So the point is that there's a very simple way to get rid of these candidate p-form symmetries. Just add new states. So that topological linking that I just mentioned, where you have a symmetry over here, linking with a defect like this, you can destroy the linking. So you can destroy the linking or how it's acting by just adding a new state into the theory. And this state might be very, very heavy. So it's something you may not know about as a low energy effective field theorist. But at some mass scale, you add this new state in, and then the linking is gone. Why? Because I can just pull it over to the side, shrink it down here. It doesn't act anymore on the defect. So what would I add in the context of these geometric Cobordisms that we were talking about? Well, what we're imagining is we have this original Cobordism. So we build a cone kind of going in this radial direction involving our manifold. But rather than let it kind of persist forever, we're going to add a new state or a new Brainer defect into the system. This is something that's not present in the supergravity theory, but we're just choosing to add it in to get rid of the candidate global symmetry. And you should be thinking about it as similar to this. We add these new states in to destroy the original linking that we had.
Silly question, but it's like an orientation reversal defect.
Yes, I'm going to talk about those in just a moment. Yeah. So in fact, those are going to be the only ones that I talk about in just a moment. But yeah, so orientation reversal is totally fine as a candidate defect. Yeah. OK, so here we go. We have a cone and we have some defect like this. And so what's the mileage from this? Here's the conjecture. The point is that in practice, you can't hand this to a mathematician. They'll just say, I don't know what you're talking about. But you can hand them the thing on the bottom. You say, I'm going to give you a mathematically well-defined Cobordism group with some specific structures that I want to talk about. And with respect to those, go out and compute the Cobordism groups. If you get a non-zero answer, the swampline Cobordism conjecture is saying, all right, you need to add that defect, that new thing, into the system as a new dynamical object so that the kind of supplemented theory doesn't have any global symmetries. So you're predicting new objects whenever you find these non-zero Cobordism groups. So what am I going to do today? So the script G in this case is going to be referring to these so-called spin-twisted duality bundles. So what we're going to do is we're going to be considering cases where we have a spin structure, a duality bundle structure, as indicated by these two pieces of the connection. And then there's going to be this correlation between the two, because the Is there chalk? Or... Oh, I see. Yeah. I see it. Because the thing we're going to be interested in is fermions that live in sections of spin cross some candidate gamma mod Z2, where in this case, gamma is just going to be this pin plus cover of GU tilde. Okay. So what we'd like to do is calculate the corresponding Cobordism groups. And just to kind of jump ahead, we're going to see that in some cases it is non-zero. So this is going to predict for us the existence of new kinds of brains. Okay. Now today, I'm not going to do it for every choice of Cobordism groups. I'm just going to focus on so-called omega k equals 1. So the first Cobordism group. What does that mean? That means that the boundary spacetime is just going to be a circle. And we're going to have some complicated duality bundle over that circle. So we're going to be imagining just some circle like this. And it's going to be, because this is omega 1, it'll be a codimension 2. In general, it's a codimension k plus 1 object. So it's going to fill all but 2 of the directions in the d-dimensional effective field theory. OK, now here is the claim. It turns out that the first Cobordism group of this thing is just the abelianization of GU tilde plus. Morally speaking, the reason to expect this is omega 1 is basically associated with like a first homology group. And if you remember back to, I don't know, your topology classes or whatever, if you have, say, the fundamental group of a space, the abelianization of that is just the H1. So morally speaking, this is why you ought to expect this. And you can prove it. So just to remind you a little more, what is an abelianization? You start with the original group. You look at the so-called commutator subgroup. It's defined by looking at all the commutators, group theory commutators that look like this, GH, G inverse, H inverse. And then you just look at the subgroups swept out by those kinds of commutators. And quotienting by that thing, you find this so-called abelianization. One way to think about it is you just start forcing everybody to commute, and you get a smaller group out as a result of that. So even though GU tilde plus is a very big, nasty, complicated group, by the time we're done with it, the only thing we're actually going to care about is the abelianization of it, which is going to turn out to be a very small and friendly group. OK, so here is what the abelianizations look like. By the way, you can also do it for just the reflection piece and just the spin lift piece. I'm not doing that. I'm just going straight to the final piece of it. Here's what you get for all the different U-duality groups. As you can see, there's always this Z mod 2. And that's the part I'm going to focus on. These ones are associated with an internal reflection. So if you remember that d-dimensional torus, it's going to correspond to an orientation reversal of that d-dimensional torus. These here, these extra Z mod 2s, have to do with the fact that they have an SL2. SL2 is basically different in a subtle way from all the other factors that we have here. These Z mod 2s are more associated with certain kinds of supersymmetric branes and backgrounds, and I'm not going to talk about them unless you ask me about it. I'm going to focus on this kind of common Z mod 2, which is present in all the different dimensions. So what's this thing? What is it doing? Here's what it does. So remember that we had this geometrization of the U-duality groups in terms of large diffeomorphisms and T-dualities. This is what this thing is doing. So let's geometrize that duality bundle in terms of a d-dimensional torus fibered over this S1. What's happening as we go around this, this defect here is that the d-dimensional torus reverses orientation. Okay? So in other words, it just flips its orientation in this particular way. So that's why we're referring to it as kind of a reflection brane, as we're about to see, because it corresponds to an internal reflection on this internal torus. So now what I'm going to do is tell you some properties of this codimension 2 brane that we're getting straight from the Cobordism conjecture. So we'd like to know some properties of it. So that's where I'm going to head next. The stable, non-supersymmetric RP brane, where again, R refers to the fact that it's a reflection on the internal directions of this torus. OK, so it's a codimension 2 thing. And so remember, we have M theory. It's on this space. The big D and little d add up to 11. And what you can do is you can consider the reflection in, say, the ith direction. So you can consider a reflection on any of them, but it doesn't matter. Just as long as you have one of them, it'll be fine. And I'll refer to that as R sub I. And this is what it does. It sends the d-dimensional torus to its orientation reverse just by sending this thing here. So if you look at, for example, the volume form, d theta 1 wedged d theta 2 all the way up to d theta d, it's just flipping the sign of that. OK. So here's an example, reflection 6 brane and T2. So this is some 6 brane, or it fills 7 space-time directions. So we have M theory on this R9 times a 2 torus. And inside of this R9, that's our 9-dimensional effective field theory, we're going to have some 7-dimensional defect. Here's what a reflection one brane looks like in terms of an element inside of GL2Z. So remember I told you that you have SL2Z, and you add a few more generators to get to GL2Z. Here's what the reflection looks like, -1 and 1. So what it's doing is it's just you'll imagine you have the torus as a square. It's just flipping either this way or this way. OK. So I can do it either this way, or of course I can put the -1 down here. Doesn't matter. So what are some properties of this reflection brane? If you go through it, you can show that it's actually non-supersymmetric. So sorry, do you have a question? Or? Yeah, yes. So this is like tau goes to minus tau bar. So it's what's that? So tau goes to minus. Yeah. All right. I can only go forward. All right. Right. So you can have -1, and you can also have the -1 here. So both are included. If you just have this one, it's enough because you can also do conjugations by SL2 elements to move it around to the other one. So in other words, take this one and then apply an S-duality transformation to switch the A and the B cycles of the torus, and then this will be down here in terms of the -1. So all you need is one reflection, and then you can sweep out the rest of them. But of course, it'll be interesting to ask, as we will later, what happens if all the reflections are interplaying with one another simultaneously? Yeah. OK. We're back. So precisely because tau goes to minus tau bar for a 2 torus and related statements, you can show that these branes don't preserve any supersymmetry. So they're non-supersymmetric objects. Okay? So that's the first exciting thing, that this Swampel-Adam-Cobordism conjecture is telling you about a non-supersymmetric object. Perhaps even more surprising is that it turns out that these things are stable against deformations into supergravity fields. How could this possibly be? How can I write down a non-supersymmetric object which is stable to degrees of freedom in just the low energy effective field theory? Well, I told you that it was a Cobordism defect, and so I can't just smooth it out to something that's characterized in terms of a smooth manifold in the low energy effective field theory. If I could, then it wouldn't be a generator of the Bordism groups to begin with. It had to be singular from that point of view. So this was actually argued in this paper here. I'll review that in just a little bit more detail. And we actually looked at this in some related contexts shortly after that. And another interesting thing that we know about it is we actually do know some things about the world volume degrees of freedom living on the reflection brane via so-called what are called BPS lasso arguments. So I'll explain. I'll mainly focus on these last 2 bullet points to illustrate some of the things we do know about these kind of non-supersymmetric objects. Yeah.
Does it mean nothing?
It depends on whether they're the same reflection or a different reflection. So if it's the same reflection, then yeah, it's not quite nothing. It's more just like it's topologically trivial. So it will just decay into just gravitational or in other kinds of radiation modes. So of course the stress energy will still be there because that's going to still be present. But if you look at, say, somebody winding around, they won't see the Z mod 2 charge or anything like that. So there'll be no charge left over from the thing. Yeah. So why is it stable? Does there exist a deformation to Sugra fields, supergravity fields? The answer is no. Why? Because the Cobordism group we already calculated was trivial. If you could smooth it away using the fields of the effective field theory, you would have been able to demonstrate just directly, just build the configuration directly in the supergravity theory, and you would have been able to show that no, you can actually deform this thing away to kind of nothing at all. That's not the case. So at least in terms of these modes, it's stable against such deformations. So you might want to say, well, there's some unknown deformation to some other thing in the UV completion I don't know about, but I will lump that in as being the same kind of object as this. So in other words, no matter what you do, there's some remnant floating around that you cannot get rid of in the low energy effective field theory. What are some properties? Let me now move on to BPS branes ending on this thing. OK, so here is a picture of a lasso. So this is something I just grabbed from the internet. So this is a piece of rope, and the idea is that you throw it around a steer or a cow, and you pull it, and it gets tight. So we'll see how that happens in just a moment. Let's consider a reflection around, say, the first direction of a d-dimensional torus. we have this kind of reflection. We have S1 getting sent to S1 bar. So just orientation reversal on the first S1 factor. A natural question to ask is, what's happening to the modes of M theory when we do this kind of reflection? So for example, the three-form potential is actually a pseudo three-form potential. What that means is that when you do the reflections on the different directions, there is an additional minus sign relative to what you would have had if you just treated it as an ordinary real three-form. The reason you have the pseudo three-form property is because of in M theory, the M theory action has a coupling that looks like C, wedge G, wedge G. And in order to keep this coupling preserved, you actually require that there's an additional minus sign getting picked up from this. So what this means is that if you look at reflections, say on the first direction, and the mu nu row legs are all distinct from one, then it picks up a sign. And if one of them is like that, then it picks up a plus sign. Is there a question? Or? Okay. Okay, so in other words, what happens now if I start talking about branes that get wound around this thing? Well, consider M2 branes, which are not in the one direction. So in other words, they're just all in different directions other than the one that's getting reflected from the first direction. Because of the branch cut coming through, remember this is a codimension 2 object, two M2 branes can come down like this and can encircle or enclose the reflection 1 brane. What does this mean? This is a lasso. It's the rope is tightening around it. It's tightened up, and then you can see that two M2 branes can actually terminate on the reflection brane itself. You can actually sharpen this argument to argue that a single M2 brane can end on it. I'm not going to go through that here, but some of that can be found in some papers I can tell you about later. So in other words, two M2 branes, if the M2 brane doesn't wrap the internal circle that's getting reflected, they can end on this reflection brane. Similarly, you can have an effective string, not the fundamental string. The fundamental string would be an M2 brane that's wrapping the circle getting reflected. If you have, let's say, a T2 or a T3, and you wrap on one of the other circles of the T2 or T3, then one of those effective strings can also terminate on the reflection brane. And you can play similar games in the context of, say, what happens with M5 branes or Kaluza-Klein gravitons or things like this, and whether those things can terminate. That corresponds to, so what you're thinking about, so in type 2b, there's, okay, so let's go back to the F theory torus. There's two things you could talk about in type 2b. One is a reflection like this, and one is a reflection like this, okay? So one of them is indeed orientation reversal of the world sheet. That would be like omega. That omega is not to do with Cobordism, it's just the usual world sheet orientation. There's another one having to do with left-moving fermion parity. So the one I'm talking about right now is left-moving fermion parity. You can also talk about omega in, say, type 2b and so on. That would be like, let's now talk about like the type 2b reflection 7 brane. That would tell you, for example, that a fundamental F1 string can terminate on the reflection 7 brane. Yeah, exactly. And so in other words, because it's the -1 to the FL, all of the D branes are charged under this -1 to the FL. And so what it's telling you for the type 2b reflection 7 brane is that all the D branes can terminate on it. Now, if you do it instead with with omega instead, what you'd find is that the F1 string can terminate on the reflection omega brane, but the D1 string does not, and so on. So you have choices here. But indeed, you know, when I start going to T3, T4, the distinctions will start getting blurred because which one is the M theory to 2A circle that I want to talk about. So I'm just giving you some examples of the kinds of objects that can end on it. Yeah. Okay, now because this object can end on your reflection brane, you actually know something about the degrees of freedom that are on that brane. Consider a gauge transformation associated with that thing. So this brane that we're talking about, it's a K brane. It's coupling to a K+1 form potential. So there's gauge transformations like this. In order to maintain gauge invariance, there has to be a compensating degree of freedom on the brane itself, which compensates for this thing. Otherwise, these gauge transformations would break this thing. So if you go back and you review your kind of string theory 101 notes, I don't know, maybe 102, and you look at a string ending on a D brane, how did you know that the D brane had a gauge field living on its world volume? You look at the B field, the 2-form coupling to the string. You look at the gauge transformations of that. It's D of a 1 form. How do you compensate for that? You introduce a corresponding mode on the brane itself, which cancels off the gauge transformation. So there's actually a large number of degrees of freedom living directly on this reflection brane. All of this kind of is suggestive and suggests that there might be a non-supersymmetric conformal field theory living on the reflection brane, in particular a higher dimensional non-SUSY CFT. But at the moment, it's just kind of an interesting conjectural speculation. Why does it have to be a CFT? Well, it's got like, two form potentials and things like this. So I don't see any, I mean, I would be shocked if it kind of flowed to a trivial fixed point or something like that. So I don't think it's a gap system. And the other option is that it's a totally free field theory. I mean, it could be, but I mean, it all kind of points to it's a non-SUSY CFT, but I agree, it's not proven at this point, so I can't say anything more than that. But we're certainly thinking about it because I think it is a non-SUSY CFT. Okay, so that was for a single reflection brane. Now, what happens if you start taking multiple reflection branes? So let's decompose our d-dimensional torus into a product of a bunch of these little circles, like this. And let's imagine we have like a bunch of reflections. So R1 through Rm is just some subset of these 1 through D. So if it's an even number of distinct reflections, it turns out that the kind of endpoint of these things being near each other is a supersymmetric bound state. And I'll tell you what the bound state looks like. If it's an odd number, then again, the killing spinner analysis tells you that you're not preserving any supersymmetry. So you're getting some kind of non-supersymmetric bound state left over. Okay, so let me do m equals 2 RP branes. So that's a two-dimensional torus. And so we're going to do a reflection on this circle here and this circle here. Okay, so I already told you the answer for how these reflection branes look on a 2 torus. Here's the first reflection, -1 here and +1. And I do the S dual, so I switch the roles of the A and the B cycles. So I get a +1 and a -1 over here. Now, you and I can both multiply these matrices together, and we get -1s down the diagonal. And this monodromy is a well-known thing if you've studied F-theory. Even if you haven't, it's not too hard. It turns out that it can be related to a background of the form C cross T2, quotient by a Z2. Now, in the limit where this T2 shrinks to 0 size, this is what an F-theorist would recognize as giving you, say, if this were now in the context of F-theory, you'd say this gives you an SO8 gauge theory, 7 brane. The situation we're talking about is slightly different because the T2 is finite size typically, but it's at least going in that direction. So let me explain what this thing looks like. All right, so I'll write down a Weierstrass model like this. Again, this is just telling you about some family of elliptic curves as swept out by the y and the x coordinates, and you move around in the z directions. Basically, because of this C cross T2 mod Z2, turns out that there's 4 fixed points. Here they are on the torus. I'm taking a square torus like this. Here they are, these 4 fixed points. And so what this locally looks like near each one of these little dots is basically, since I'm really doing M theory on this T2, it's some background that looks like this, R7 cross C2 mod Z2. So this is known to give you an SU2 super Yang-Mills theory. There's 4 of these fixed points, so that's accounting for the SU2 to the 4th. And again, if you had shrunk this whole thing down, you would see an enhancement all the way up to an SO8 if you're doing, say, F theory. We're not doing that, but that's where this would happen. Okay, so that's for 2 of these reflection branes. It builds an interesting object F theorists already knew about, but the point is that if you have 2 distinct reflections, then they combine to build this interesting supersymmetric system. How about m equals 4? You can do the same thing again, where now you have a Z2 squared quotient like this. And there's a corresponding Weierstrass model, which basically involves a collision of an SU to the 4th on one locus and an SU to the 4th on the other locus. And they meet kind of in the center right here. What you find locally is basically the gauge theories that you had before, plus so-called tri-fundamental matter. Let me explain that in a little more detail. This tri-fundamental matter is coming about because if you look at the Z2 squared quotient, locally, it has this form. So let's write down the C and then a holomorphic coordinate for this T2 and this T2. It does these 2 things. There's also a third element where you basically take the product of this one and this one, so it just reflects the Z2 and Z3. But it's known that this thing gives you basically an SU2 cubed tri-fundamental. And this is what would be an example of what's called a 5D T2 theory. If you do it for the higher Z2s beyond just these, then what you get is actually so-called 5D CFTs with big flavor symmetries, so-called 5D TN theories. For this case, it's a bit boring as a 5D CFT. It's not really interacting. It's just some free hypermultiplets. But they're in a big representation, an SU2 cubed of this thing here. And then you glue these local pieces together to get the corresponding system. How about m equals 6? Do the same thing again. T2 times T2 times T2 now is Z2 cubed. And now we have a collision of 3 of these things. Here's what it looks like. They're all kind of meeting in this kind of big hit right here. I'm not doing a great job drawing all the different intersections, but the point is you get gauge theory plus matter plus new kinds of interactions. Locally, it looks like this kind of quotient, C4 mod Z2 cubed, and here's the different reflections that generate the whole thing. You can, of course, take different products and so on, and so you get all of the other singularities that you had before, plus new kinds of interactions. So it looks like some 3D n equals 1 theory with some SU2 to the 6 gauge theory. This is just locally in one patch. And here's all the tri-fundamentals. And if you just check, they can all form gauge invariant singlets under all 6 of the pieces. The reason it's 6 gauge groups is because you just look at them pairwise and how they're kind of matching together. And this is what one of the superpotential interactions looks like in the 3D n equals 1 theory. Okay, so pretty complicated kind of bound states can form from just merging these reflections together. They're supersymmetric objects. They're forming interacting quantum field theories. So all of that is very nice and suggestive. Okay, what if it's odd? If it's odd, we can say less about it just because we don't have supersymmetry, so it's harder to kind of access the degrees of freedom. But this is part of the reason why I'm expecting there is an interacting theory typically floating around, because you can kind of vary the number of, you can start stacking the non-supersymmetric reflection branes to go between supersymmetric and non-supersymmetric. What does it look like? Geometrically, it looks like the supersymmetric bit we had before. So a T2K, so an even dimensional number of toroidal directions. And then you times it by another Klein bottle. This is a Klein bottle at infinity. So remember what a Klein bottle is. Instead of having the orientation kind of glued to preserve it with this circle in the fiber, what we do is we reverse the orientation to go around. So this S1 infinity is the one in the kind of space-time. And then as you wind around it, the circle in the fiber goes upside down. So this S1 fiber flips orientation when we go around. That's accounting for this up versus down here. And then you build a whole cone over that thing. Geometrically, the cone looks like, again, so when I mean cone, I mean this thing here. And we have some Klein bottle and some T2K quotiented by appropriate group. Okay. So I think I'll start wrapping up. So conclusions and kind of future directions. What was this talk about? So I told you about several things, one of which was this pin plus lift of U dualities, which I call GU tilde plus. And the motivation for doing this was several. One was just what happens when we don't have supersymmetry, we don't have spin backgrounds, how do we talk about U dualities in these broader settings? What we saw is that we can actually calculate the first Cobordism groups of the spin-twisted duality bundles. What we found always is that there's a Z2 reflection. And using the swampland Cobordism conjecture, that directly tells us about the existence of a new non-supersymmetric stable brane, this reflection brane. And we looked at, for example, some of its properties, what can terminate on the brane, what kind of degrees of freedom it has, and also what kinds of bound states these things can form. And we saw that in many cases, if you take an even number of these things, you get interacting supersymmetric bound states if it's an even number of these reflection branes. And it's probably some non-supersymmetric interacting system if it's an odd dimensional, it's an odd number of these things. So using the usual arguments about having decoupling limits, there is a quantum field theory living on this reflection brane. I think all the indications are that it probably is a non-supersymmetric CFT, but of course the evidence for that is kind of not totally solid, so it'd be nice to kind of strengthen that. And then another very natural direction is to look at computing the corresponding Cobordism groups for higher K. So in the context of, say, 2B dualities and other U dualities, you can play the same game where you look at the higher values of K to see whether you're getting new kinds of objects from the predicted by the swampland Cobordism conjecture just from having this higher K. And it would be very interesting to kind of do that because it would kind of give you a nice sweep through the kind of non-perturbative structure of those d-dimensional effective field theories as well. So that's all I wanted to talk about. So thanks. I'll stop here.
Thanks very much for the very nice talk. Are there questions from the audience? Yes.
Can you see that in the supersymmetric cases, the tensions of these objects agree with what you would expect, at least in the SUSY case? Is that obvious?
No,
Like
it's,
for these
it's not obvious.
concepts?
So one of the things that we also want to do is calculate, for example, the tension of the reflection branes themselves. So because they're not supersymmetric, we don't actually know, say, the deficit angle generated by them. The reason why it's non-trivial is that there's both the tension of the reflection brane, but then there's also a binding energy between the two. And so the combination of those three pieces is what's producing, say, the tension of, say, the SO87 brane and so on. So we're thinking about it right now, in particular because it's stable, or we think it's stable. We're trying right now to figure out like what are kind of valid backgrounds to kind of extract the tension. But yeah, so we don't know that, and so I can't directly answer, but we are thinking about it. Yeah.
So I have one quick question. So you were stating these branes are stable.
Yes.
Did you say anything about this today? Maybe I missed it. Rather than stating it in some page.
Yeah. So here's the argument. So the point is that if you could smooth it away inside of just using the effective field theory, then you could actually turn the whole argument around and say the mathematician must have given you 0 for the Cobordism group. But so in other words, if you just look at the manifold and there was a way to smooth it away in the effective field theory, there would be a way to smooth away the manifold or the singular manifold you were talking about in the Cobordism group. That's not happening precisely because once you get a non-zero value for this, it means there is no smoothing available to kind of get rid of the defect, period.
So anything you can predict from such a non-vanishing of the Cobordism group would be then stable in this sense then.
Right,
Yeah,
exactly.
okay,
So that's a lesson I had not appreciated before kind of this paper appeared. Because, for example, when we wrote down an earlier paper where we looked at kind of finding the reflection 7 brane in the first place, our first inclination was that, well, it's non-supersymmetric, it's probably unstable. And the intuition there was, in other contexts, say like the D7 brane of type 1 string theory, that one is unstable. And what does it decay into? So that one corresponds to just decaying into a flux inside of the kind of ambient SO32 gauge theory. So it dissolves into a flux, right? So it dissolves into a field configuration of the effective field theory. This is different because it's not being captured in the same way. There is no kind of, it's basically always staying as Z mod 2. It never kind of embeds inside of a U1 or as a continuous gauge field configuration. So yeah.
But D7 brane also arises in this way for the other.
No, so it doesn't come from a first Cobordism group calculation. So the way you get it is basically by just looking at boundary conditions for like type 1 string theory. And if you look at the corresponding Cobordism group, that one does not predict anything. So you can still characterize properties of it, but it does not show up as a Cobordism. So that's the big distinction. And the reason it doesn't show up is, again, because that one can be smoothed out into a gauge field configuration. So you can think about it as like you started with a particular codimension 2 flux configuration in SO32, and then it smooths out. This is basically like taking like a broken U1 and then taking the limit where the Higgsing scale has been sent off to infinity. So there's no way to kind of turn it back into kind of a dissolved flux from that point of view. And again, the point is that like the Z2 from this -1 to the FL is kind of intrinsically discrete. It never embeds inside of a continuous U1. And so for that reason, we can't smooth it away. Yeah.
Yeah, thank you. Other questions? Oh, yes. Yeah.
I'm just a little bit confused. So once you know that the Cobordism group is non-zero, you also need to show that your background represents a non-trivial Cobordism class, right?
Well, so the background we're going to talk about is going to be a singular configuration inside of, say, M theory. So the question is, can the effective field theorist see that? And so what the effective field theorist is going to see is some singular configuration in terms of the field profiles. So it's going to look to them like there's some singularity of some kind in their space-time. So at that level, it's kind of beyond the effective field theory. Does that make sense?
But maybe I'll ask later.
Okay. Okay. Thank you.
Any other questions? So I don't see any further questions. Then let's thank Jonathan again for the nice talk.